So in other videos, we've discussed data structures that represent sets in an approximate way, or that allow us to find the cardinality of a set in an approximate way. Now we're going to talk about the CountMin sketch, which is a data structure that helps us to count the frequency of items in an input data set. So there's a counting aspect to what we're doing here that we haven't really been doing yet. We've been sort of flattening things into sets, but CountMin is able to consider the frequencies of the different items in the set. And we're going to tackle this in a series of 3 videos. So in this first one, we're going to talk purely about how to add things to this sketch and then how to query this sketch in the sense of a so-called point query, trying to ask how frequent is a particular value in a data set. In the next video, we're going to prove something about how close our estimate is going to be to the true frequency of the item in the input data set. And then in a third video, we'll talk about some other issues like how this can be thought of as a kind of linear transformation and some other things like a different strategy for updating the CountMin sketch. Okay, so let's get started. And let's talk first about sort of the problem setting that we're in. So again, our input is, we might say a data set, or we might say a stream. It's a sequence of values that are coming at us. For the purpose of this discussion, we're going to call them A1, A2, up to AM. And each of those AIs, each of those items in the stream, is from a universe of size n. And so, the number of times a particular value x appears in this stream is called its count, or its frequency, and we'll use the notation f subscript x to be the number of times the value x appears in the data stream. It's the number of a sub i's such that a sub I equals x. Okay, so let's just take a quick example, make sure we understand what all these variables mean. So let's say we're in a scenario where the stream is a stream of zip code digits. So zip code just being part of an address, it's a series of numbers. Right, so these are some digits from a zip code. And it being a zip code, we can say what M is going to be. Okay, well, for this particular example, right, I've got 212.182.682. There's 9 items in that stream. So we can say, okay, well, in this example, M, which is the number of items in the stream, equals 9. Okay. The universe size n, so we're saying for each of these digits, how large is the universe of values from which it could be taken. And in this example, because they're just digits, 0 through 9, we're really just talking about the size of that set, which is 10. So n equals 10. And then let's pick a couple of values. So let's pick the value 1, for example, which obviously does appear in our stream. So f sub 1 is just the number of times 1 appears in my stream. So there it is twice. So f sub 1 is 2, and then let's do f sub 2. 1, 2, 3, 4 is 4 2s. Okay, so just a small example. Small data set, small universe, small frequencies. But of course, we're generally going to deal with very large data sets drawn from a large universe with potentially large frequencies. Let's describe this CountMin sketch data structure. So the CountMin sketch data structure is going to be sort of a cousin to the hash table and a cousin to the Bloom filter. But it's going to have the shape of a matrix. All right, so it's a matrix of counters, and all those counters are initially set to 0. So this, just like with the Bloom filter, for example. So this is an example of an empty CountMin sketch. It's a matrix, it has rows, it has columns, but initially each of the elements is set to 0. Okay, so just a few more words about this matrix. We are very used to, from talking about hash tables and from talking about Bloom filters, of thinking of the hash function as taking input items and assigning them to, let's say we've got a hash function h, and assigning them to a particular bucket, right? So the hash function is sort of spreading things out like this. It's spreading things out sort of vertically, or at least the way we've been drawing the picture so far. The hash function is spreading things out vertically. when we look at this matrix, we have to think of it as almost like taking the picture that I just drew and sort of this vertical thing and bloop, turning it sideways, sort of rotating it like that, so that now the buckets are arrayed like this, and the hash function is picking not a row of this data structure, but a column of this data structure. Okay, so let's be more specific, and then we have different rows for different hash functions. Okay, so let's say that associated with the first row of this matrix, we have a hash function called h sub 1. And when we apply h sub 1 to an item in the input stream, maybe the first item, which we could call a sub 1, that hash function is going to take the input item and map it to a particular column in that row of the CountMin sketch. So for a sub 1, let's say it maps here. So if we are inserting a sub 1, what we would do is we would increment this counter by 1. You can see that's still 0 back there, but I'm just drawing a sort of +1 to indicate that's what we would do in the process of adding a sub 1 to this CountMin sketch. We would increment that counter by 1, but we're not done because each row is a different hash function. So now let's go on to the second row. For the second row, we would apply a second hash function, h sub 2, to the same data item, still a sub 1. And h sub 2 would map a sub 1 to potentially a different column compared to h sub 1, right? They're different hash functions, so it's not necessarily going to map it to the same column. So here it's going to this column. So again, what will we do when we're inserting a sub 1? We will increment that value by 1. h sub 3 similarly sends it to a different column. h sub 4 similarly sends it to a different column. And I won't always want to write out these 4 different invocations of the hash function, so sometimes I'll abbreviate it by just putting h once and then putting 1, 2, 3, and 4 as sort of like a set-wise subscript for h. All right, so h sub 1 is mapping a sub 1 here, h sub 2 is mapping a sub 1 here, etc. Okay, so once we actually do these 4 increments on this CountMin sketch, which was initially empty, we're of course going to get 1 here and 1 here and 1 here and 1 here and zeros everywhere else. So here's what that looks like. So here's the state of the CountMin sketch after adding 1 item. Okay, great. So now let's add a second item. So that was a sub 1. Let's go on to add a second item called a sub 2. Now again, I'm using this shorthand where I'm just writing the hash function h, I'm just writing that symbol h once, but then I'm putting a set in the subscript, meaning I'm going to use hash function h sub 1 in the first row, h sub 2 in the second row. So in this case, the hash function maps a2 to here. Okay, so a different column from a sub 1. This was a sub 1 went here. A sub 2 is going here. A sub 2 is going here in this row. So h sub 2 is sending a sub 2 here. H sub 3 is sending a sub 2 here. The same happens to be the same spot that h sub 3 assigned a sub 1. So there is essentially a collision in the third row. Okay, so a sub 1 and a sub 2 got mapped to the same column in the third row. And then h sub 4 maps a sub 2 here. So let's go ahead and do those +1s. Now the state of the CountMin sketch after having added a sub 1 and a sub 2 looks like this. I've got mostly zeros, but then I've got some 1s, and in this row I have a 2 because there was a collision there. And then in the final row again I have 1s. All right, let's just add a third item, a sub 3. Now I'm not even going to draw the arrows, just so that to make the slide a little cleaner. So let's say that hash functions h sub 1, 2, 3, and 4 map a3 to these highlighted elements, right? And so when we're finished with having added a1, a2, and a3, our sketch looks like this. Okay, the most recently updated items are highlighted in blue. Okay, so obviously as we were adding items, we were incrementing some value in each row, and sometimes we were incrementing a value that was already non-zero. In other words, we had a quote-unquote collision between 2 of the items. Okay, now let's think about once we've added items to this data structure, and now we want to ask the data structure, for this query item, how many times did it occur in the input data set? What would that look like? Okay, well, as usual, the thing we'll do with the query is we'll apply the exact same set of hash functions to the query as we would to something that we were trying to insert. And those hash functions are going to send us to particular elements of the CountMin sketch, right? In each row, the hash function will send us to a particular column. So for this particular query, q sub 1, the hash functions are sending me to this element in the first row, this element in the second row, this element in the third row, this element in the fourth row. And so the first question is, what should our estimate be? Right? Our job is to estimate how frequent this item q sub 1 is in the input data. So what should our estimate for f sub x be? And I'm putting a little tilde over the f just to indicate that it's an estimate. Okay, so what should our estimate tilde f sub x be, given that these are the values that we encounter in the CountMin sketch in the rows, in the elements pointed to by the hash functions? Well, it should be 0, right? There's no way q sub 1 could possibly have been in the input data set. If it had been in the input data set, then these couldn't possibly be 0, right? They would have been incremented at least once, right? So the fact that any of the elements that we saw was 0 tells us straightforwardly that q1 was not ever seen among the input items. So in this case, our estimate for f sub x, tilde f sub x, should be 0. Okay, so even though we're going to report 0 as the answer, we had these non-zero elements here, right? We had non-zero elements in the second and third columns. So why did we have those non-zero elements? Well, because of collisions, right? Other items that really were in the input data set collided with q sub 1 in rows 2 and 3, right? So how much of what we see here in these highlighted elements is due to collisions? Well, all of what we see in rows 2 and 3, right? The 1 and the 3 are there because of one collision that happened in the second row, and 3 collisions that happened in the third row. 3 items from the input data set collided with q sub 1. And when I say 3 items, that might be 3, in theory, it could be 3 copies of the same item, right? The 3 collisions doesn't necessarily mean I collided with 3 distinct items. It could be just 3 copies of the same item, or 2 copies of one item and 1 copy of another. Regardless, I'm just going to say that's 3 collisions. Okay? So these are definitely all of these counts, this count of 1, this count of 3, all of that is due to collisions. Okay, new scenario. So that was query q sub 1. Let's move to a different query, q sub 2. And let's say that the hash functions map q sub 2 to these elements in the 4 rows of the CountMin sketch. Now what should our estimate tilde f sub x be? Okay, well this time there's no zeros, right? So I can't argue that that item definitely didn't occur in the input data set. Instead, what do? I've got 1 here, 3 here, and 1 here. So what should I report? Well, I think I should report 1, right? Because 1, right, everything is greater than or equal to 1, right? So all 4 of these are greater than or equal to 1. This one's greater than the others, right? But that doesn't, that can't possibly be that q sub 2 was in the input data set 3 times, even though there's a 3 here. Because if it were in the input data set 3 times, then these would also all at least be 3, right? Instead, they're less than 3, right? So if I'm going to produce an estimate, I'm going to just take the minimum of all the items that I'm seeing here, right? And that would have worked before too, because the minimum was 0 in the previous case. In this case, the minimum is 1. So what I'm going to report as my estimate for tilde f sub x is 1. And let's ask that same question we asked before. How much of what we see here in the highlighted elements is due to collisions? Let's ask separately. Let's look at the 1s first. And let's ask, could these be collisions? right? I'm not asking about this element. I'm only asking about these 3 right now, the ones that are all equal to 1. Could those 3 elements be collisions? In other words, maybe Q sub 2 was not really in the input data set, but it just happens to have collided with other items in those 3 positions? Yeah, that's possible. You know, it's always possible, right? This is very similar actually to when we were talking about Bloom filters, and we asked, could we still have a coincidence of k collisions if we had k separate Bloom filters with k hash functions? Yeah, that's still possible. Obviously, it gets sort of less and less likely as we increase the number of hash functions, but it's possible. So those could be collisions, yes. By contrast, if we look at the 3, we can make a stronger statement. There's definitely collisions there, right? If Q2 were present 3 times, then these would also all be 3. But because it's not, we know that there were 2 occasions when another item collided with Q sub 2 in that 3rd row. Okay? But the key that we've now explained by looking at these 2 examples is that if we want to report our estimate, tilde f sub x, what we do is we take our query item, we hash it in every row, and we take the minimum of all the values that we see. Right? This is why it's called the CountMin sketch, because an inherent part of how we query it is we take the minimum of all the elements that we see. Okay, so before I wrap up with some statements about how good the estimate is, let me show you another example of a query. So the kind of query that we were just doing, we were given a particular item, and we were asking how frequent is this item in the input data. That's called a point query, right? Point because we're trying to get the frequency of one item. Another kind of query another reason we might be building this CountMin sketch, this matrix of counts, is because we want to find what are called heavy hitters, which is to say we want to find frequent items in the input data set. So this comes in different forms. This could be items whose frequency, whose count, is over some threshold, or it could be the top, like the top k, the top n most frequent items in the input data set. 2 different versions of the same kind of question. So how would we use a CountMin sketch to keep track of these heavy hitters, or to ask whether something is a heavy hitter? Well, it's not too hard, right? Because as we're adding things to the CountMin sketch, let's just imagine this is the state of a CountMin sketch after we've already added several items. And now we're adding a new item, x, the next item in the data stream called x. And it goes to these values in the CountMin sketch. So we increment all those values. Well, in the process, it would be very easy for us to additionally just ask the question, well, how frequent do we think this item is that we just added? You know, essentially, what would a point query tell us about the frequency of this item? And in this example, you can see if we just take the minimum of all the elements that we just updated, 10 would be the minimum. Right? So if our threshold, for example, for whether something is a heavy hitter or not is that it has to occur at least 10 times, then we might, at this moment, decide that we want to add the item x to the set of potential heavy hitters. If instead we are trying to find the most frequent items, like let's just say we're trying to find the top 10 items, the top 10 that are the most frequent, well, we probably need to keep another data structure in addition. So we might need to keep, for example, like a heap data structure, where not only are we able to keep track of the counters in the CountMin sketch, but once we see that an item might be a candidate for inclusion in the top 10, we have a way of checking whether it's already in the top 10. We have a way of checking whether it really is better than one of the existing top 10, right? So we can use a heap to do that. So that's another common application of this CountMin sketch. There's point queries, and then there's sort of the heavy hitter problem where we're trying to find the most frequent items. That's a very common need. You know, you can imagine you're trying to find the most frequent words in a corpus of text, or you're trying to find the people who are sending data to each other most often on a network, right? Identified by their IP addresses or something like this. Okay, So now let's think again about our point query strategy, and let's just put together a little bit more notation and thinking about what it is we're doing. What it is we're doing when we're taking the minimum as our answer to the point query. Okay, so first of all, this is our CountMin. Let's just say this is a sort of picture of our CountMin sketch again. And let's just say the number of rows is we'll denote with the variable d, and the number of columns we'll denote with the variable w. And then, of course, each of these particular elements is a counter, so let's give all those names too. Let's say that, for example, the counter up here in the upper left-hand corner is 1, 1. It's like row 1, column 1. Row 1, column 2, row 1, column 3, etc. Right? So these are just different counters corresponding to what's the value in that element of the matrix. Okay? In terms of how we added things to the CountMin sketch, we can also phrase it that way, right? So the actual count, ci, comma j, for row I, column j, is just the number of items that were mapped to column j by hash function I, right? We're talking about an item in a particular row I, so we just need to focus in on just the hash function I. That's the only one that matters to row I. And j is the column. So this is just the number of times some item in the input data set was mapped to column j by hash function I. Okay. Now, let's think about a particular item x. And let's just say for a particular item x, item x mapped to that particular element in the first row. Okay? And so let's refer to that element in the first row as c, right, for count, c sub 1 because it's in the first row, comma h sub 1 of x because this is the column that hash function 1 mapped x to. Okay, great. And now let's say the other hash functions map x to these other columns such that these are the 4 elements of this particular CountMin sketch that x gets mapped to. And so, of course, our answer to the point query is going to be the minimum of all these items. So let's give that a little notation too. So our answer to the query is going to be the minimum for I from 1 up to d, in other words, for all the rows. It's the minimum across all the rows of c sub I, comma h sub I of x. All right? So up here we had c sub 1 of h sub 1 of x, but here we're saying our answer to the point query is going to be the minimum over all the rows of c sub that row, comma, hash function for that row of x. Okay? So this is just what one of the rows tells us. This is the minimum of what all the rows tell us. And so now a quick question for you is, what's the relationship between these 3 quantities? The 3 quantities being, here's what we get from the first row, here's what we get when we take the minimum over all the rows, and then here's the truth. This is the true frequency of x. Okay. So what is the relationship between these 3? They're going to have this kind of less than or equal to relationship. Well, let's first just think about the red and the blue, just this min and then the c sub 1. Clearly, since the min is over all the rows, and this is the value in just one of the rows, this one has to be at least as large as this, right? The minimum over all the rows can only go down with respect to the count in a particular row. Okay, so we know that this minimum is less than or equal to this count. Now, the true frequency is the true frequency. It is unaffected by any collisions, right? It's the actual true frequency, the f sub x, right? This is not, I should say, when I write f sub x, I'm not saying f tilde sub x, right? I'm saying f sub x is the true frequency of x. All right? So collisions can only make the estimate for x go up, for f of x go up, right? Collisions can only fool us into thinking that the count is higher than it really is. Okay? So since these over here are just estimates that are affected by collisions, this is going to be less than or equal to either of these 2 things. So now we can put the 3 things in order. Okay, so f sub x is the smallest, the next largest is that min, the min c of I comma h sub I of x over all the i's, over all the rows. And then this count, the count we get just from the first row is over here. Okay? Right, so the thinking here is that this is affected by collisions. This removes some of the effect of the collisions, but there can still be collisions in all D rows of the CountMin sketch. So this still is not necessarily the correct answer. And the correct answer is only ever less than or equal to these estimates, since the estimates come from using a hash function, and hash collisions can only inflate the estimate. It can only make the estimate too high. Okay, so these are the essential aspects of the CountMin sketch. When we query for a particular item x, we take the minimum of the elements that are selected by the hash functions, separate hash function for each row, and that estimate we would call tilde f sub x, and then collisions can make us overestimate the true frequency f sub x, but not underestimate. So tilde f sub x is greater than or equal to f sub x. But how far is it? That's really the key question. Can we argue that we're not too far off? Or in other words, can we argue that tilde f sub x is probably not too far from f sub x? And that's what the whole next video is about, is can we prove something useful that says that tilde f sub x is probably not too far from f sub x?